Okay, so we have this very nice dictionary now that we've essentially completed from our work this morning. So if you remember here this morning I had the, if you like, the dictionary for just the closed string sector for how T-duality works, right? So now we can add to that, and I won't write it out again, but we can now add to that some of the things we observed. Some of the things we observed this morning. The key thing that came out of all of this discussion was really that Neumann and Dirichlet boundary conditions turn into each other under T-duality. Okay? And essentially that's telling you, I have an open string, I have the ends need some sort of specification of a boundary condition. It's either Neumann or Dirichlet, and now we know what happens. If you have one, then it turns into the other, and vice versa. You can sort of see that schematic, well not schematic, you can see that precisely from the fact that essentially whether a condition is Neumann or Dirichlet comes from whether I take the sum or difference of these two derivatives. Okay? And so in the picture we've been discussing before, you either have a Neumann condition on the plus combination or a Dirichlet condition on the negative combination. And so that's why they're swapping back and forth. It's really simple from that perspective. So we should list that. Right? So T-duality. So Neumann boundary conditions turn into Dirichlet. Things that we associate then with gauge field information turn into information about positions. And I gave you the precise formula for that. Field picture. So let's just say information. So this is, you know, in the say in the direction we're T-dualizing it, then so we were taking the 9 direction, for example, then this would turn into a position about what's going on in the X9 information. So then we have this picture which I drew in the end of this object, which I explained why it's called a D-brain. And so it has, wow, these pens have so these pens have wow. These objects that are defined by the fact that strings can land on must in that Dirichlet direction. So these directions are the Dirichlet boundary conditions, and then the directions that are, if you like, in the world volume on Neumann boundary conditions. And so then I end up with the idea that I have a dp brain where p is some integer. And that comes from saying that's from specifying Dirichlet boundary conditions in the telling you about where the brain is in the transverse directions. Okay, so that's the language, so there are a number of different directions I can go in now, so I have to make some choices because obviously I can't tell you all of them. But one other thing I wanted to summarize then is essentially the statement I made and motivated that these are really dynamical objects because the fluctuations of the string, if you think of the fact that the string is defining where the brain is but the string is fluctuating, then those fluctuations define the fluctuations of the whole object itself, right? Which in the old soliton language you would call the collective dynamics, the massless modes. Describing the fluctuations about the default position. And so, as I said, those come from simply looking at our friend, the photon, in a different way. Right. So, if I have mu, still working with the example where I have just the 9 direction is what I tisualize, so I have a D8 brain. If I have mu equals 0 up to 8, right, this defines some gauge field that just has some U1 associated with it. And the language that's used then is that that's a U1 that's sort of living on the world volume of this gauge theory because it exists in these 0 to 8 directions, and it's what you would think of as a gauge field. The other one, the missing component of psi 9, right? That's also a massless field, but from the point of view of the 9 reduced directions, the 0 to 8 directions, it's just a scalar, right? And but it's in the spectrum as well. So so this is a scalar, which let me just call it phi. No, let me not call it phi because dilettante. Let me call it. What do I want to call it? Let me call it phi, lowercase. And that phi is charged under the U1, but its job is to tell you essentially, as I said, where the brain is in the transverse directions. Okay. So you can see what's going to happen if I tisualized 3 more times. Okay, I'm going to end up with, for example, a brain with 5 extended directions, and those 3 now internal components of the gauge field would be 3 additional scalars. And that makes sense because I need 4 scalars to specify where I am in the 4 transverse directions that the brain exists in 10 dimensions. Does that counting make sense? Yeah. So the story, that story just continues. So we can then, so I guess I should say that, so in general then, have some U1 on a single D brain. Hopefully you did as you promised at the end of the lecture, and you went away and convinced yourself that it's a UN on N coincident D brains. Okay, so I have D, if I have, let's try and do the count. Well, okay, maybe I should get you to do the counting. So how many, I'm in 10 dimensions, so how many Dirichlet conditions do I need to specify a DP branch? Say again? Are you including the fact one of those is time?
9 minus P.
9 minus P, right? So I have 9 minus P Dirichlet directions. D directions. I can't spell. Okay, that will also translate into 9 minus P scalars. Right, so let me give the scalars an index, I. And if you like, you could call them transverse scalars. Well, let's just call them scalars. And a P plus 1 dimensional Yang-Mills, right, U and gauge field. Okay, so I'm not doing a lot of calculations here because we've done the calculation, right? The calculation was that basic mass spectrum that we computed for the open string spectrum last week. In some ways, this has just reorganized it in some way, in a way that makes it much more geometrical. These are scalars in the adjoint. Right, and the scalars in the adjoint of the UN simply because they're really just internal components of the gauge field, which is in the adjoint of the UN. So we haven't really done anything to touch that. Okay, and then now you see how to complete the exercise I was telling you about. I was saying that geometrical picture I was drawing where I had multiple D branes, I had 2 of them, was just like the adjoint Higgs mechanism, right? And you can see giving a vacuum expectation value to those scalars will adjoint Higgs. The UN to the end. Okay, so hopefully that picture is clear. Are there any questions about that? That's a lot of the dictionary laid out for you. There's several pieces now I want to look at in more in detail about what to do with these dynamical objects. We've seen that they're dynamical objects. If someone says, in a theory of gravity, I have a dynamical object, what's the first thing you ask? Okay, you could ask that, but I would ask a much more direct question. I'm in a theory of gravity, and I have a thing that can jiggle and move around.
Metric tensor.
What?
Metric tensor.
No. You're all way too sophisticated.
Newton.
What?
Does it reproduce Newton?
Well, we know it reproduces Newton, but what would Newton ask?
Mass.
Yes, what's the mass of this thing? Yeah? It's the most basic question. So I have this object that I've told you now is not sort of a boundary condition in space-time. It's a real object that can flop around and move. I want to know how much energy does it cost me to do that? Yeah, I want to be able to understand its mass. So that's what we need to figure out. How do I measure the mass of this thing? Yeah? So again, it's going to come out very quickly that it's all built into the technology of the string theory already. So let's talk about that. So it's a mass, really what I'm talking about is a mass per unit volume. right? Otherwise known as a tension, right? So it's some extended object, and I need to compute its tension. So the computation of that is actually rather nice. It will take me further afield to show you all of the elements, but you actually have a lot of the intuition already to hand from some of the things you've been seeing in other discussions. And again, this is again another example of a computation that's as old as the hills, but with a new perspective, you sort of can extract new information out of that that old computation. Okay, so let me. Okay, maybe I'll come back to that. Maybe that's something I should have done first. Okay, actually before... Sorry, I'm sort of, there's a bit of a dilemma as to what I should do first. No, okay, I set up the mass discussion, so let's do the mass discussion. So here's the thing. I have a D-brain. Here it is, sitting here minding its own business. And then, as we've seen, in some sense, by construction, I have an open string an end on it. Now, I'm not going to, for now, worry about the other end. We'll get to that, okay? So do what you want in your imagination with the other end. I'm interested in this end for now. Okay, but here's a thing that is definitely a process that can happen in the string theory, right? Which is that the open string is perfectly free to do a one-loop process where it goes and comes back and just goes around in a loop. Yeah? That would seem to be a very basic diagram that I should be able to draw. So there's the end of the string. So in the end, my diagram for that open string is a cylinder. Right? That seems to be something I should be able to compute in principle. The technology of string theory should tell me how to do that. But before we go and compute, let me tell you why this diagram is interesting. What I did just now in my discussion is I told you about thinking about this diagram with time running this way. Okay? But now let me say, well, if you just walked into this room and I had this diagram and I didn't have this arrow saying time running this way, you would have been perfectly within your rights to say, oh, this is some tree-level closed string process with time running that way, right? And as we know from our intuition and field theory and what have you, both things are true, okay? But what does that mean? That second interpretation means that what I have on the one hand, I have a one-loop open string process, but on the other hand, I have just this object that's just emitting some closed string quanta. Right? What are some of the most basic closed string quanta we're familiar with? The graviton, right? So that's exactly how we would measure the mass, right? What do I mean when I say something has mass? It interacts through gravity. At the quantum level, it's emitting and absorbing gravitons. So now we know exactly what the calculation we must do in order to compute the tension of this thing. I mean, it's emitting a bunch of other stuff too, right? Basically all closed string stuff in principle. We'll get to that in a moment. But that's the core diagram that we need to compute. Are there any questions about that? That's sort of a hugely fundamental diagram in all of this. Okay, so this is a one-loop diagram, and it's extremely similar to set up to the partition function discussion that you had this morning when you were discussing the heterotic string theory with Narayan. you have, right, you're essentially tracing over this process. You did that for the open string, sorry, for the closed string at the torus level. This is an open string at one loop level. It's a cylinder diagram. You can do pretty much the same words will come out. So then there's a set of limits you can do to just focus. In principle, everything that can possibly propagate, the entire tower of closed string states will propagate along here. And we don't care about most of them. We're really interested in the coupling to gravity in order to compute the tension. So there's a way of computing that whole partition function and then actually focusing just on the low energy sector. Essentially, essentially you focus on the limit where this this cylinder is long and thin. And to actually make the computation nice and straightforward, the textbook computation actually says, well, why don't I measure the interaction between two identical D-branes and compute in that way? So I'm going to tell you a couple of things that you extract from this diagram without actually doing the computation, because it would take us. I mean, we could do it in this lecture, then we wouldn't have time for anything else. But I'm going to tell you some of the things you extract from it. But you know, you should definitely in your notes write down that important observation that this one loop process is going to generate the tension. So let me, having said that, I realize I've just been cruising along without. Okay, good. So this diagram yields two, actually, very important numbers. And I need to tell you why, and then it links to some other interesting piece of information. So, here's the thing. I'm just blanking for a moment on what I was going to say. Excuse me. Oh, yes. So you can compute an amplitude, which is this diagram. And I actually wanted to tell you that the result is very simple. And I wanted to see if you could guess what the result was. It's a very, very simple formula. What the answer is for computing that diagram, that we're going to get all of this amazing information from. Yeah, I'm asking you. Because your intuition might actually guess what the answer is. Remember, it's a vacuum diagram in a supersymmetric theory. Zero. Okay, so we're done. That's the answer. Okay. I'm being a little glib here, but there's a very important lesson. The reason it's zero is for the reasons I just said. It's a vacuum diagram in a supersymmetric theory. Fine. On the other hand, it's zero. The way it's zero is actually interesting, and we know how the zero must be organized. And so what happens is that, and I'm really, really sorry, I don't have time to tell you about it in detail. But what happens is that the stuff that all cancels to zero, actually due to a beautiful 19th century identity, you can actually go in and see what the different sectors of the string theory it's coming from. And again, you know how to do that. And please go away and look up this calculation. It's in the notes I alluded to before. You can because we know how everything is built, right? right? In the string theory, from oscillators in the various ways, in the various sectors, and so on and so forth. So, for example, etc., and then also from the Ramon sector, which gives us the Ramon stuff, and the Schwartz stuff. Remember all of that discussion we had on Friday. You can actually keep track of all of those pieces in the calculation. Okay, and so the reason why this cancels to zero goes to zero is because it's a cancellation between two sectors. And this is where I wanted to get to. And so the zero results from cancellation between two kinds of exchange. I have states which are in the Nova-Schwartz. Remember, this is the closed string sector now, right? So things are in the following setup. I have Nova-Schwartz stuff, just looking at the bosonic sector, and I have Ramon stuff. And so it's a cancellation between Nova-Schwartz exchange, which includes stuff like this. And Ramon exchange. And so the reason I'm pointing this part out is because it leads us to another hugely important fact in the whole discussion. And that is, so this is G, so this includes the C's. C1, C2, etc. I guess I should be also C0. So why is that interesting? Well, this is another way of saying a very important observation, and this was the observation I was referring to that Polchinski made precisely 20 years ago, which is that D-branes are what are called BPS states. So have you met the idea of BPS states before? No? Okay. So so I'll say a little bit more about what that means. But from the point of view of what we're doing here, there are a very special sector of the theory that allows you to, if you can compute the BPS spectrum of some theory, is extremely useful because for various reasons it's protected under various deformations that the theory can have. What that means, especially for discussions, for example, like duality, is that if you know the BPS spectrum at weak coupling, it's going to be the same spectrum at arbitrary values of the coupling. Okay, and so one of the wonderful things about D-branes that is being revealed by this calculation is that they're BPS states, and some of the things we're going to write down from this calculation, some of those properties then, are properties that we can trust at arbitrary levels of the coupling. And that's useful because you want to be able to sometimes say things at strong coupling. Your usual perturbative techniques don't apply at strong coupling. But if you use those perturbative techniques to say something about the BPS states, you know at least that sector will still have those things true at strong coupling. So when Polchinski observed that that means D-branes are BPS states, that completely opened up the whole understanding of what was going on in strongly coupled string theory. Because finally we had some objects for which, if we made computations, we could trust those computations at strong coupling. So that's where I'm going with this in making these observations. So here is a good. So one of the first things, let me recommend then, before you start worrying about BPS states and some fancy string theory, go back to your field theory studies and look at some of the simplest field theories that have, so you need extended supersymmetry. So go back and look at some model of extended supersymmetry in a Yang-Mills theory, or just U1 gauge theory. And what you'll find is that there's a special sector of BPS states there that are studied. So BPS stands for Bogomolny Prasad Sommerfeld. Okay, so I'm saying a bunch of things, giving you a lot of information, but it's because there are a whole bunch of interesting concepts that are coming out at this point. The basic thing you'll see in any of these BPS discussions is the fact that these things have some mass and in appropriate units, that mass is equal to some charge that those objects carry. So I put that in quotes because, you know, what does that mean without, you know, some sensible normalization? What's going on here? So a good example, yeah, here's a really good example which I strongly recommend. You've all done some version of general relativity and maybe studied black holes, right? A really nice example is to study the Rising and Nordstrom black hole, which is a charged black hole, in a supersymmetric theory. So a good example. The Rising Nordstrom black hole in n equals 2 supergravity. And in fact, so there's a nice literature on that, and I think I give references in the notes I gave you. The reason this is kind of nice and intuitive is because you have this nice picture of the fact that this thing has a mass which you can read off from the metric, and it's a mass, and it has a charge, which is basically how much charge does it have in the f squared sector. So there's, you know, there's this part of the action, and there's this part of the action. Right? And it has mass and it has charge coming from those two sectors. And what you can do is actually worry about what happens when I take a Rising Nordstrom black hole and another Rising Nordstrom black hole and ask, what force do they exert on each other? Which is not an unreasonable question. And of course, due to the fact that they're gravitating objects, they should attract. Yeah? So there's an attractive force. But they also have the same charge, and there's a repulsive force. And in general, one is going to win and the other is going to lose, depending upon the details. Now, when embedded in that theory, the units work out such that precisely when they are Rising Nordstrom black holes, those things exactly cancel. And so another way that people talk about BPS states is that there's states for which there's a no force condition. The exchange due to the gravity sector cancels the exchange due to some sector that they're charged under. And hopefully now you see the analogy with what's going on here. So so the force cancels due to gravity balanced by electromagnetism. So this is a really good example to have in your head when considering this setup here. And in the sector that we're interested in, the thing that tells us about mass, of course, is what I was saying before, the exchange of gravity. And then the thing that you then discover must be going on is they must be charged under some analog of electromagnetism. And this is precisely what we anticipated in this morning's lecture, that these guys are carrying Ramond-Ramond charges. So they're BPS states, and analogous to this, these guys are carrying some gauge charge, okay? Gravity's cancelling electromagnetism. Here, we can look into the details of string theory and seeing that gravity from Nova-Schwarz exchange is cancelling something from this sector. Someone over there this morning asked the question, what's the point of this sector? Why is the string theory carrying this stuff around? And now we see why, or at least this is suggestive. The D-branes are charged under this Ramond-Ramond sector, and as they must be because they're being exchanged in this diagram. It's being sourced by this D-brane, picked up by that D-brane. Okay? So all of this stuff is being interpreted from this A equals 0 result. Okay? And as I said, the point is that you can slice this 0 up precisely because you know how the states are built. You can slice it up to see what's Nova-Schwarz and Nova-Schwarz exchange, what's Ramond-Ramond exchange, and in what, in the limit, focus on the zero mass sector. So are there any questions about that? I'm going to tell you the results now. What I need to tell you essentially is, in saying mass equals charge, I need to tell you what the mass is and what the charge is. So that's what I'm going to, I want to give you some precise numbers because these are precise, fully, in the same way I said, look, that Newton's constant that we had, that's something we compute from first principles in the string theory. So this is telling you how in first principles to compute the mass and the charge of these branes. I want to give you those numbers because they're going to be useful in other places. Yes?
So there is no branes without the Ramond-Ramond field?
Not in this simple setup. Yeah. And what we'll see is that for every Ramond-Ramond field that we've seen, there's just the right brane to source it. I mean, you can already kind of see the counting because I basically have all the right ranks of the fields that are possible. And you can run ahead and see that I have odd rank in type 2A and even rank in type 2B, and then under T-duality, the branes will change their dimensionality by just the right amount. I'm kind of giving you all the punchlines, so let's write it all down. But that's where we're getting. Okay, so in interpreting the computation, I need to write down the effective action for the brane. I need to be able to say how is that tension going to appear. So I need if you like, some analog of the Nambu-Goto action that I wrote down for a string. Just want to make sure I have all the normalization right. But essentially, what it'll have outside, just with the string theory, it'll have a tension, yeah, and that's the thing we're trying to compute, and then it'll have some fairly, the first thing you might guess is some geometrical action, and you'd be correct, and so let me write it down. So I need to so here's the deep brane. Okay, it has some p plus one-dimensional world volume action. Yeah? Not action. World volume. And so I should have an integral over such a thing. I could give it some world volume coordinates, just in the same way that I gave the string some world volume coordinates, tau and sigma. Right? So it's p plus one-dimensional. I'm going to call those coordinates, I always forget whether that's xi or zeta. That's xi. I'm going to call those coordinates xi. Is that right? Yeah. And then I'm going to have some analog. I'm going to have some analog of Nambu-Goto here, which would be that determinant that I think you discussed. And then I have GAB. And I'm going to leave some room here, but at least from the point of view of gravity, I certainly have this term. So what is this thing? This, and if you go back to your notes on Nambu-Goto, you'll see this is exactly the same action. Okay? This, in fancy language, in unfancy language, it's the induced metric. In fancy language, it's the pullback from the space-time, blah, blah, blah. The point is that I have the following You did this before with Nambu-Goto. right? I have some space-time G, okay? The x's as a function of xi are, if you like, a family of maps telling me how that object is draped in the space-time, how it's embedded in the space-time, right? And then this tells me how that space-time metric appears on the world volume. Right? If you go back and look at your Nambu-Goto, this is exactly what you wrote down, even though you may not have thought of it in those terms. Okay? And then there's so this is sort of a little poor language, but this is what's used. Is that you form the metric. The metric's called GAB. You form the metric, which really shouldn't have any indices anymore. And then you form the square root of the determinant. Okay, that will then give me some action that computes the volume of this thing. The world volume as it sweeps, as the thing sweeps out as it moves in space-time. And then that action tells me minimize the world volume, and the prefactor is the tension. But by dimensional analysis, that's really all I'd expect. Yeah, that's all there is. Any questions about that?
Where does this effective logic come?
My head. No, but it comes from basic physics, right? It comes from, I have an object with tension, okay, embedded in space-time, and it's trying to minimize its volume.
Yeah, but looking at the initial string theory, this is an effective action, it not be a description of lower energy of higher theory.
Yeah, but along the lines I just suggested. So we discovered this object that has tension, and we don't know what that tension is, but we know unless physics has gone crazy, well, it's gonna minimize it. Yeah.
But we started with a string theory, theory with one dimensional.
Right.
And this is new ingredients that come from consistency.
These are ingredients that we had. Yeah. Sorry. Finish your thought.
By recording consistency, these new ingredients. But this is just in order to take consistency. I mean,
Consistency of what?
of everything. Everything goes.
So as I was saying this morning, it isn't that everything that people had been doing was wrong or inconsistent, right? They just hadn't turned on all the things they could turn on. So what we're discovering, right, and this is the lesson from the 90s, the big explosion of interest, is the fact that, if you like, string theory is not a theory of strings.
It was hiding.
Yeah. String theory can, we started out defining string theory with these strings, right? And indeed, a weak coupling, that wasn't a bad thing to do. And what we'll see, there's one more ingredient I'm going to tell you, which is another reason why we missed it. And because in some sense, these things are already telling us how to get beyond weak coupling. So the discovery then is that, there's a whole bunch of sources in the theory that we hadn't turned on. And that's perfectly fine. Doesn't mean that there was something missing from before. You had set them to 0. And now we're learning how to turn them on. Yeah. So there's one extra ingredient I need from this to see, to complete the intuition that I've been building for you. And that is the fact that I can also make a guess as to how this thing talks to the dilaton, the other massless field that is propagating at the lowest level. Okay, and the reason I can tell you exactly how that must appear is because I can also stare at this diagram and go, what order of perturbation theory is it at? And now you see why I did this digression this morning about the order number and e to the dilaton and what have you, right? Because I can see that this is a one loop in open string, one loop in string perturbation theory. It's an open string one loop diagram. Okay. If you go back to what I was showing you this morning, that means this is of order string to the -1. Just looks like that. Okay? So again, this is something you can read off. I'm not just making it up. So you can read off from what we said. And so with this thing moving in the background fields given by some metric and some dilaton, you can write that as the effective action on its world volume in order to go ahead and sort of proceed with some of the things we're going to do. Actually, for the point of view of turning, of computing in just the tension, you can actually just have that dilaton frozen to a constant. Yes.
For the annulus, yeah, if you're doing preload again.
Oh, I'm sorry. Yes. Yeah. Sorry. There's this and there's that. It's this square. Thank you. Yeah. What's being pointed out is that this diagram, this whole diagram is at this order.
No, 0, 0.
No, you're right. You're right. You're right. It's the same level as the torus. You're right. Yeah. Thank you.
Yeah, the way it works out because of propagator, it goes like 1 over these things.
Yes, thank you. There's the propagate. Yes, thank you. So, so I have G string to the 0. Okay, and the point, just looking at the factors then, this, and this is what I was actually going to write down next, so I would have found my error anyway. Thank you. The point is when we go down to the limit where this diagram becomes, as I said, a very thin cylinder, what I actually end up doing is comparing to a field theory diagram. And then we're just doing our usual phenomenology, right? And so we have a contribution from the vertices and a contribution from the propagator. So here, this is an open string disk diagram of order G string to the -1. That's controlling the strength of the emission or absorption of the graviton. So that should be telling me what order of perturbation theory the tension is coming at. But thank you for helping me undo my error. And then the graviton exchange then. Good. Yeah. Okay. So at the end of the day, that's the world volume action. So from talking about the coupling to the gravity side of things, I've left some pieces there I'm going to get to in a moment.
So
and then
-5 or -2.
As written. Yeah. Right? Because the tension, I have one factor of the tension controlling, yeah, and then another factor. This, yeah. But then there's got to be another piece which is telling me how it controls how it couples to the Raman sector. Okay, and then this is where we get to use that other thing I was telling you about this morning, when we were asked from over here, what's the point of these guys? How do they enter the theory? And I said, well, they would be the natural things to integrate over the world volume of the D brane. So I have a P plus 1 dimensional world volume. All right. So the natural thing would be C, in the notation I've been using, would be CP plus 1. Okay. And then I'm simply saying whatever that thing that's outside, which I called E last time, that's the charge. Okay, so that's the charge of the P brane to this thing that's naturally integrated over its world volume. It'll turn out in more complicated examples, some of the lower and even some of the higher C's, higher in rank, can couple to this P plus 1 dimensional world volume But if the D brane is just sort of doing not much, but just kind of sitting there in space-time like that, this is all you get. So at the end of the day, we're in good shape then to sort of see how this works. I can decompose the string theory. There's a whole bunch of string theory junk which I can identify as exchanged from the Ramond and Nuber-Schwartz sector. I can isolate those two pieces, thing cancels against thing. I can take both pieces into the field theory limit by shrinking, going to the limit where this cylinder gets very thin, okay? And then I essentially then have everything I can just read off from this diagram. And then I can compare to, because now I'm sort of down in field theory, I can now compare to, compare the string theory result to these coefficients here and just compute what those things are. So it took me a long time to explain that, but it's sort of a core organizing piece of the story. So I wanted to make sure you understand it. There's a bunch of formulae. You can look that up, and I think you're all very good at differentiating and integrating and things like that. So let me not tell you how to do that. Now I think you're motivated to understand it. I think it will be clear how the computation works. So do go and have a look in the appropriate papers. So the result at the end of the day is as follows. Make sure I don't write things down wrong. It actually turns out in the normalization we're using to be a very straightforward set of numbers. Let me also get the numbers that I had before. Sorry, I just lost my place in my notes. Excuse me. Oh, that's very embarrassing. Okay, here we go. So let me write it in a way that's kind of the summarizing of the mass equals charge result. Okay, so mass equals charge in this language, the extra factor is a factor of the string coupling that floats around. Okay, but that aside, we're getting that these two things are equal, and I've written it down there for you. And then it's 2 pi to the minus p alpha prime minus p plus 1. This part's just dimensions. And that's the result. Good. So, yeah, I think in view of the time, I won't go into. I won't go into the rest of the couplings for the Ramond sector. Yeah, I think that would take too long. Okay, so let me say a couple more things, and this is a little further afield than I can go in today's discussion. But it turns out, I hate using that phrase, but there we go. It turns out that this full thing's often called the Dirac-Born-Infeld action. turns out that the rest of the theory comes in that way. You know there's got to be also some Yang-Mills sector, or at least some U1, and one way of seeing that this is the U1 we were talking about is simply to expand this this action. And at leading order, you'll see that this actually is, our friend 1/4 f squared. So there's an interesting exercise. Expand this, say, in a flat background to make it easy. So that leading order in alpha prime is actually -1/4 f squared. So some of you may have encountered Born-Infeld because it's actually a famous example of an attempt to write down a nonlinear electromagnetism theory of nonlinear electromagnetism. What we're seeing here is that the string theory naturally knows about that. If you start with our leading order discussion at lowest order in an alpha primed expansion, you get Yang-Mills theory, which is what we've been discussing. It actually gets correct as an infinite set of corrections in alpha primed that corrects it up into this determinant of, essentially determinant of 1 plus f sort of action, which is called the Born-Infeld action. So, I'm sorry, there's just not enough time to explain all of that. I think I might have a little, if it turns out I have a little time, I can actually show you how you can prove that using T-duality. But the steps are just going to take a little bit more time than I want to spend. So anyway, I can leave that there. So I may revisit that shortly. But for a lot of what we do, we tend to work at leading order in alpha prime, and we just write down some 1/4 f squared for the at some Maxwell sector, or we go non-abelian and it's some Yang-Mills sector. Yeah. So are there any questions? I said a lot of words and drawn a lot of things pointing at other things.
That C term is a sum is inside of the action, or?
Yeah, I'm integrating a p plus 1 form over a p plus 1.
Okay, so you're calling the determinant of something. No, that's
Not sure. This term?
This M, yeah. This is part, yeah.
Yeah, so this is the generalization of integrating A over the world line of a particle with some charge E, right? That was it was your question. And so, yeah, there it is, right? Now we see the point of those fields C. So what would happen in the old days is people would say, oh, the supergravity has all of these fields, but let's just turn them all off, because what do we do with them? And now we see that they have natural sources, which are the D browns. Actually, that reminds me, there is a very important consistency check I want to discuss, and maybe I should discuss that next. That may be more important than showing you the Born-Infeld story. Yes, actually I should do that. Okay, so there's something else that I claimed on Saturday that is a piece of this story. It's very important. But let me list. Keep this. So let me list. So D branes are BPS states. D branes are BPS states. D branes carry Ramond-Ramond charge, which is what enables them to be BPS states. And I need to say just a little bit more, because there's a potential problem that we need to get out in front of. So let's make sure we understand it before someone presents us with it on the street.
The Raymond charge is the new B.
Because that's from the Ramon concept. So, remember, after we went into all of that detail, we constructed the closed string spectrum, right? So for example, we ended up with saying, 8 vector, 8S on one side, and another copy of that, or the 8C, and we tensored everything together. We basically did 8 times 8 equals 64 several different times, and we constructed the full Bosonic spectrum, right? But then I said, oh, wouldn't it be interesting, wouldn't it be kind of fun to present things in the following way, right? So what did we first discover? So we had the even C's in type 2B. And then we had the odd C's in type 2A. Okay. And then I said, oh, well, why don't we just, through Hodge duality, write down all the other C's we could define by Hodge duality. In other words, if I have something electrically charged under this, under these, and that's exactly what this is, right? This is what we would think of as being electrically charged in some generalized sense. Then did I do that right? I've done something wrong. Sorry, I'm just going crazy there for a moment. Oh no, this is right. Yeah, I'm just missing that. Right, this guy turns out to be self-dual. Right, your old is torturing me. You all have this in your notes. I wrote this down last time, right? Yeah, and so, so do you remember this, first of all? Right, and did you go away and check that the statements I made about Hodge duality, the ranks did work out and everything? Let's just pretend you did. Right. Okay, yeah, so what I've shown so far is that, at least from the point of view of the way we've done things so far, I can see that I have, these guys are electrically charged under, they're carrying electric charges of these C's. But if I have electric charge, for example, this, I also have magnetic charge here, right? Just generalizing what you know about electromagnetic duality in 4 dimensions, right? So there's an important consistency check that I need to check, which is hugely important because it could blow apart the whole theory, right? If you remember, Dirac, way back in whenever, right? Dirac showed us that if I'm in a quantum theory, if I have some electric charges, okay, and I have some magnetic charges, they can't be arbitrary. They actually have to be related to each other in a precise way that makes the quantum theory consistent. Consistent. Okay, so these are electric charges, So now I'm going all the way back to, undergraduate electromagnetism here. But it's the same story. Electric charges have magnetic charges. And if you remember, he demonstrated this. He demonstrated this by constructing a magnetic monopole. And there are many ways you can do that. It doesn't matter how you construct that magnetic monopole. If you then move an electric charge in the background of that monopole, or a monopole in the background of that electric charge, okay, single valuedness of the wave function, again, will tell you that the product, E, and I'm not going to get the numbers right, E times G is some integer times some numbers. I'm not going to remember. Do you remember this?
2 or 1/2.
Sorry?
It's either 2 or 1/2.
What's like 2 or 1/2?
The thing in the parentheses.
Well, there's numbers like h bar and c squared and things like that. Those are the numbers that mean, right? Yeah. Okay. And then n is an integer. Okay. And good. Right. So we don't worry about that a lot in everyday life because we haven't found a magnetic monopole, right? But if we did, Dirac tells us that its charge had better satisfy this. Why am I banging on about this thing? Well, we're in a slightly richer position in the string theory, which is that by finding things that are charged under, as I said, say a D. So I would have. So tell me, what D brane carries that charge?
E1.
Right. So I have a D1 brane here, carries the electric charges of this C, right? What brane carries the electric charges of this guy? A D5 brane. Okay? According to our calculation, we have both D1 branes and D5 branes in the theory. Okay? These D5 branes are monopoles of this C2. Yeah, and these D1 branes are monopoles of this. We've already computed their charges. We don't have any room to change those charges. So we better check. We better redo the Dirac calculation, right, which is had already been argued how that would work just in general. How do you spell technical? Is it like that? Is that right? Okay, and I guess it's next. They already wrote down, just in general, if I have extended objects, they generalize the Dirac conditions just for fun. Okay, but now we actually get to use it here. Okay, so what I'm saying is that if I have both D1 branes and D5 branes in the theory, as this is telling us, and we have the explicit charges, we had better check that that quantization condition is satisfied. So this is another nice computation that you can do, and you can sort of check how it works. And if you think about it, it's a condition on the product. So consistency. I'm saying a lot of words, not writing them all down, so I hope you're making notes. Consistency says that the mu p and mu 6 minus p, that would be the analog. Did I do that right? Yeah. Right? Had better be n times some basic quantity. And again, in view of the time, let me not go through it, but let me tell you what that basic quantity is. Should essentially be some more powers of 2 pi. Well, we can just multiply, right? Maybe we can but that's the check. So, sorry, I apologize because I'm having to skip some topics. I'm easily losing my place in the notes. Okay. Okay. Here it comes.
Sorry,
Yeah,
number 6. Is it okay?
I think it is.
Why is there 6? Say, shouldn't be 8. 8?
What's your calculation?
I don't know, the church, the monopole, I don't know, it's done.
Well, okay, well, no. That's very good. Rather than me wasting time finding a number that you can look up, let's make sure we understand where this comes from. Agreed? That's more useful. So I have a DP brain. Actually, you're going to do the calculation. I'm just going to write what you tell me. Okay? So I have a DP brain. Which Ramon field? Right, so C, P plus 1. Yeah? So what's the field strength of that? Right, so that's going to go to G, P plus 2. Yeah? So now I homodualize. What do I do? What rank do I get? Right, I take P plus 2 away from what? How many dimensions am I in? 10, right? So this is going to go to G. So this is Hodge star. So this goes to everyone. We're all on board with what we're doing. Now homodualizing this thing. Okay, let's slow down because some of you are looking confused. Let's just remind ourselves what we do in 4 dimensions, right? So I have the gauge field A1. Yeah, I form F2. I homodualize. That gives me F tilde 2. Yeah, and then that would have been D of A1 again with a tilde, if you like. It's a little degenerate in 4 dimensions, because yeah. But that's what it is. So let's continue this. So right, that Hodge star means I take this away from 4. So I just take this away from 10. So that leaves me with
8 minus B.
Thank you. Right? And
7 minus B.
so that would have been the field strength of what?
7 minus B.
7 minus P, C, 7 minus P, which is carried by what? 6 minus P prime. Yeah? Thank you for asking that question. That's much more important. So there's some number we can look at. Right? Okay? So here's the thing. Also in that amazing Polchinski paper from 1995, September, whatever it was, which is very brief, he showed this stuff. He unpacked this calculation, blah, 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 but he also realized he should check this. Okay, and if you do the computation, you basically put P equals P in there, right, and then put P equals 6 minus P in there, multiply those things together. You can kind of do it in your head, right, and what you'll get is this number, okay, with n equals 1. And why is n equals 1 important? It could have been any integer and we would have been happy. But n equals 1 means that they not only carry the Ramon-Ramon charge, they carry the smallest possible units of Ramon-Ramon charge. Had they carried any other units, well, they couldn't carry any smaller units, except 0, but we've already seen that they do, right? So this is really important. Okay, so this other important piece from the story. It's the minimum value. They have the minimum value allowed by the quantum theory. So they have the minimum mu p.
So under,
Yeah.
under no circumstances can it be greater than n equal 1.
No, I mean it could have been, but now we know that's just 2D brains. right? So that's really very nice, because in some ways they're telling you they're the fundamental sources of Ramond-Ramond charge in the theory. If I find something made of Ramond-Ramond charge, electrically sourced by Ramond-Ramond charge, there should be a perspective in which I think it's just made of d-branes. Yeah? This is going to be hugely important when you come to ADS-CFT and some other areas of the theory. The whole business of counting the entropy of black holes, the other stuff that string theorists hold up there as a tremendous success, all comes down to knowing that in some corner of moduli space, I can make some black holes. I can make them Ramond-Ramond charged black holes. That means I know how many d-branes they're made of. And all I need to do is go and count in string perturbation theory how many d-brane states there are. And that's the entropy. Yeah? And you know that that answer is absolutely robust because d-branes are BPS states, but even more important in a way is that they're the smallest units of charge, of Ramond-Ramond charge in the theory. And so your job is done. They couldn't have been made of anything else. There couldn't have been some secret thing hiding in there whose entropy you didn't count, because those things could not have been made of anything else. So this last thing here seems like a minor little consistency check, but it's kind of the foundation of a huge amount of entire fields of string theory. And so that's another reason why I wanted to make sure that you knew that.
I have a small question.
Yeah.
What carries C0 charge?
Ah, very good. What carries C0 charge? Well, what would be the answer?
D minus 1.
D-1. What is that? It's actually an instanton. If you like, it's localized in all directions and time. And if you think about your intuition, going back to when you did field theory, that's exactly what an instanton is. So it's called a d-instanton.
A gravitational instanton in 10 dimensions. I mean, is that what you said, or an instanton? Or what?
I mean, okay, think about what an instanton is in field theory, right? You go to Euclidean space, and then you look at something that's localized fully in Euclidean space, and also in time. So that's what this is. Because I have Dirichlet boundary conditions in all directions, all nine plus 1. Yeah. Okay. So okay, so so this lecture is kind of degenerating a little bit into listing facts, but for which I apologize. But I'm actually doing a little more than that. I'm actually telling you how to drape those facts on calculations that you can already do. We actually did all the hard work in those 2 lectures on Saturday, carefully getting the string spectrum right and showing you how to do those computations. And all I'm doing is I'm showing you the output of some of those things. Okay. So the next thing I wanted to do, which is going to set up something else, is the fact that, well, okay, so now we go back to some of the answers you were calling out back when I said, okay, I have this dynamical object, and I said, what was the first thing you would ask? And you were all saying super fancy things, and I just wanted mass. Okay, so now let's hear some of those super fancy things again.
Metric?
Sorry?
Metric?
The metric, right? Okay, so again, let's go back to, now not Newton, but to Einstein. Now we know a thing has mass, okay? I'm in some theory of gravity. Okay, I should be able to write down the gravitational field of that object, but we know that's not the way to think about it. Einstein has taught us precisely 100 years ago up to 20 days, right? Einstein has taught us what we should do is write down the metric of that object. And so the Schwarzschild metric for a point mass. What's the analog of that for these guys? Okay, so that's what I want to write down. So this comes from the other thing that we talked about in the first lecture, which is now we have we want to write down the solution of the analog of Einstein's equations, right? And we wrote down the analog of Einstein's equations this morning. So this is where you would do your work now. You would start out with your analog of Einstein's equations, and you would do the amazing thing that Carl Schwarzschild did, right, months after Einstein's paper came out, and people are shooting at him. He's on, do you know this story? Right? He's on the front line in World War I, right? And he's got downtime, and he writes down an exact solution of Einstein's equations and mails it to him in a letter. It never ceases to amaze me. Right, so we want to do the analog of that. Except that this is charged, it's a charged object, so it's going to be more like the analog of the Reisen-Nordström solution. Yeah? But morally speaking, it's going to be pretty much the same sort of thing. So what I need to do here is see, yeah, let me not write out, let me trust that you're taking notes, and you're in, so you have the action for either type 2A or B. Okay, actually the same, we could also for type 1 too. Right, so you have S, and now I need the 10-dimensional action is equal to 1 over 2 capital squared integral d10 x, etc., etc. Right, so you wrote all of that down. So what I can do is I can write down an ansatz for what this, what the metric would be. Okay, now based on what we've computed, we know what's switched on and what's switched off. Right, at some level, then I should need to write down some non-trivial metric, something for g mu nu. Okay, and then I also need to write down what the p plus 1 dimensional field looks like. Okay, and that will do the job. You could write down generalizations that other fields turned on, but for this basic result, that's all I need for the basic brain. And so I'm simply going to show you that this is something that you can understand. It's actually very similar in spirit to the Reisen-Nordström solution. And it looks as follows. It looks like this. And basically, I have space-time coordinates, which I guess I should have written as capital X. Capital X. Be consistent with what I was doing before. I have space-time coordinates, and they split into two sectors. And it's essentially the sectors that are along the world volume of the brain and transverse to the world volume of the brain. Don't worry about what H is yet. Let's just try and make sure we understand why the coordinates are split that way. Okay, I have that p plus 1 dimensional world volume, which should be red, but I don't want to deal with taking the top off one of those pens again, so right, it's red. Okay, so I have a bunch of coordinates. I'm studying now just a simple case of one of these flat brains, sort of infinite extent, a DP brain, p plus 1 dimensional coordinates. So here they are. I clearly have some nice Lorentz invariants in that part of the space-time, and so I should choose. There should be some choice of coordinates where that Lorentz invariance is obvious. So there is the the SOP, 1 acting on the world volume. That makes sense? Yeah, and then I have the transverse stuff. Now the transverse stuff, if you think about it, we've already talked about it. The transverse stuff is transverse, and all I'm doing is I'm writing polar coordinates in that transverse set of coordinates, because the whole thing is spherically symmetric, in the sense that if I think of this as a point in the 10-dimensional space-time, then I would surround it by an 8 minus p sphere. Right? So just to orient you, let me remind you what you would have done in the case of, say, the Schwarzschild black hole, or any four-dimensional black hole. You would have had some function. You would have had just a dt squared then, and then you would have had some other thing in front of r squared d omega 2 squared. You surround the point in 4 dimensions by a 2 sphere. Yeah? There's the coordinates on the 2 sphere, and then there's the radial coordinate. Right? That parameterizes the full transverse 3 spatial dimensions for a point, which would be a black hole, say, in 4 dimensions. Yeah? So this is just the analog of that. If you do the counting, you'll see it works. Okay?
So there's a dr squared.
Thank you. And then depending upon how you choose your radial coordinate, that'll affect, what the nature of the functions are here. Okay. So these are coordinates chosen such that these h's are the same. These functions are essentially the same function to a different power, and I'll tell you what that function is in a moment. But I hope you agree it's not so complicated to understand. All the things are sort of in reasonable places. So that is sort of structurally how that metric works. Let me tell you what the function actually is, h. And yeah. So h turns out to be something very simple. It's 1 plus something I'll just call rp over r. This would be the analog of the mass if this were Schwarzschild, something that's a little bit like the mass, 7 minus p. Okay, and then there's a bunch of numbers. Basically, these numbers simply come from the fact that if I were to measure the mass of this solution, it would better be some integer number times this tension. Sorry? Thank you. Yeah. And so if you work it out, so there's some numbers, and because you might need it for other classes, let me actually write it out explicitly. And then essentially a lot of the factors of pi and 2 just come from the fact that I need to remember what the volume of a surface area of an 8 minus p dimensional sphere is. Which, once upon a time, I used to carry that in my head, but I don't. So, it's a bunch of numbers, but at the end of the day, I think you can see that this is sort of not unreasonable, the structure of this. Now, it turns out, you should be able to anticipate that the charge had better get the same function involved in order to make sure that mass equals charge at the end of the day. And it enters in this way. So there explicitly is the p plus 1 form that is the Ramond potential carried by this fiber. Okay. What I've really drawn here, so that there's a really important discussion to be had here, which I don't have time for. N is some integer, and it is, as I said, the same integer that tells me basically how many units of Ramond-Ramond charge this solution has. Actually, there's one extra piece I forgot to include. I'll write it down in a moment. Okay? So at the same time, this thing is some... So now you get to think of this in the following way. Just in the same way that some mass in general relativity deforms space-time in some way, gives us a new metric, and it's some source. Okay? Well, that's what this thing is doing. So this is like a third way of thinking about what a D-brane is. We started out with being boundary conditions, and then it was some object with that effective action. But because it has mass, it can leave some imprint on the space-time, and that's what that is. Now, the strength of that imprint is controlled by how big this number is. And just in the same way in a theory of gravity, you might worry about the curvature of this space-time becoming sort of out of control. You can smooth out that curvature by making this larger and larger. In other words, you can dial up n. Yeah? And this is leading to what your next course will be about. The fact that there will be regimes where for some choice of p, this simplifies, and for n large, you have a nice supergravity solution, telling you that you can sort of trust it, and but it's also n coincident branes, n of these guys, and so there's also a UN gauge theory sitting there. Okay, and that's the basis of ADS-CFT. Okay, so just for completeness, let me also mention that these things carry a dilaton. So part of that attractive sector is gravity, dilaton, and then the repulsive sector is C. And it's e to the 2 phi is, in the way of normalized things, again, I've absorbed the background value of the dilaton, right, G string, and it's h p to the 3 minus p over 2. So I think my time is up. What do I have? 3 more minutes. Okay. Let me do one last thing. You're going to ask me more stuff about this in the Q&A anyway. Let me set up one last thing, which will help a little bit Narayan later on. Which is what I've done so far is I've mostly just considered I had one D-brane and then I had more D-branes. Okay, and we saw that that's tuning the gauge theory in the right way. You can have more D-branes of the same shape, but they're all of the same type. Yeah, and also with this really is representing the solution of n of these guys, all of the same type, in the same place, sourcing the gravity. So you can think of one of them as some sort of light thing, and then I put n of them together, and it really makes a big difference to the space-time, and I can't ignore this curvature anymore. What I didn't talk about, and there's a whole technology for that, is discussing D-branes of different types in the same discussion. Okay, and the way you handle it is you use what you basically just keep doing the calculus of open strings. That's always going to save you, because at the end of the day, it's always some Dirichlet boundary conditions and some Neumann boundary conditions. But the point is that you can come with examples where you have both Dirichlet and Neumann boundary conditions doing non-trivial things in different sectors, and you can go through and just keep track of all of these guys to see what the collective dynamics of that setup is. So in the last minute, okay, let me point you in the direction of some do-it-yourself calculations you can do. And I apologize, if I had time, I would have done one of these examples. Okay. And so, 2 examples I want to do. Okay, let me example. 2 examples. So first, I want to just list an example where I have show you how you organize all of this, and I'm going to take an extra minute. That's okay. So before we leap ahead and get confused, let's just list everything for one particular kind of brain. And I'm going to choose the D3 brain because that'll be helpful shortly. Okay. So the way I like to do things is to look at organizing how the coordinates are organized. So I tend to do this to make sure I'm keeping track of everything. So I write down all the space-time coordinates like this, and essentially what I can do, there's all my 10 coordinates. I can basically just go through and ask, where are my Neumann and where are my Dirichlet? Okay? And so I can say, okay, I have a D3 brain, for example. Okay, so how many extended dimensions does a D brain have? It's a D3 brain, it's in the title. A D3 brain. 3, right. Okay, I probably said that too fast, right? So it's 3 plus 1. So I'm using a little dash here to say that is a Neumann direction. Okay? Which means I would have specified something's wrong.
The other way
You're
around.
missing 8.
8, thank you. Yeah. It's because okay. Right, and then I'm going to use a dot to say, look, this is like telling me it needs to be at a definite position, so that's what I would say is those are where the Dirichlet conditions are. You can immediately write down, you know, these guys, right? The collective dynamics, because it basically says that from the Neumann directions here, right, I'm going to end up with a bunch of stuff coming from psi minus a half mu, which I call the gauge field. Okay? And then from here, I'm going to end up with how many scalars? 6 scalars, right? Some of you know that that's a familiar number. The n equals 1 Super-Yang-Mills multiplet in 4 dimensions, which is what this is, has this bosonic content. Yeah?
Equal 4.
Excuse me?
Equal 4.
So n equals 1 reduced to d equals 4, which is n equals 4. Thank you. Yeah. Okay. If we had a little bit more time and we trace through the Raman sector as well, we would get the 4 scalars. 4 fermions, excuse me, that complete the multiplet. Okay. But you can do it. You can just carry things out by simply organizing things in this way. And then you're just counting up the Neumann-Dirichlet boundary conditions and associating them with the creation and annihilation operators you would need to create the various sectors. So at this point you can continue. I can say, okay, I have a D3 brain, but what if I also had a D1 brain in the theory? Okay, I just made that up, right? Well, you could go, okay, where do we want to put it? Right? So I could say, let's say it lives inside, it's partly inside the D3 brain world volume, partly parallel to it. So a D1 brain. So it has that, and let's say it's lying along the x2 direction. Okay. Then it must be Dirichlet everywhere else. So now I have a new sector of strings that are added to the theory. I have this stuff, but I also now have strings that live on the world volume of the D2 brain, so that's some gauge field associated with those guys, okay, living in now the 0,3, the 0,2 directions. I have how many scalars? I have 8 scalars. Yeah? And then, but then I have additional stuff, because I also have strings that can stretch from the D1 brain to the D3 brain. And this diagram is a nice way of seeing how those are organized, right? You have, for example, 6 sectors in which you have Dirichlet boundary conditions. You have 2 sectors in which you have Dirichlet-Neumann boundary conditions, right? And then you have these 2 sectors where you have Neumann-Neumann boundary conditions, and so on and so forth. So I'm running out of time, but I just wanted to show you that this again is just the usual calculus that we have from before, but with the aid of a little bit of geometry to organize how you keep track of all the different sectors. I should stop here. I'm very rude to run over quite a bit, but I just wanted to make sure you know that technology for other areas as well. Okay, thank you.
Professor Clifford told us that, for example, a feeling space brain.
So you did talk about brains. Sorry. Okay, go on.
We have tachyons. Tachyons have negative energy.
This is in the bosonic string theory, yeah.
So eventually, the feeling brain will fall down into a point. What do you say about it? What are we studying brains?
Okay, so that's a very interesting and beautiful story, which long answers, short answers. Two things. So first of all, you're in the bosonic string theory there, right? So it comes with this tachyon that you have to deal with if you're staying in the bosonic string theory. And so one of the things people try to do is to try and make sense of what that tachyon means. Now, we deal with tachyons all the time in field theory, and we don't make a big deal about it. What we realize is that a tachyon is simply telling us we picked the wrong vacuum. Okay. So the picture that people had in mind is that the open string tachyon in bosonic string theory is simply telling us that we're on a hill. Okay, and so that instability, that negative mass squared, is telling us it wants to roll down the hill and go somewhere else. And so you expect then that vacuum decays, which means that brain you thought was there isn't really there. You create it, and it's telling you, I don't want to stay here, I want to decay to something else. And then people have spent a fair amount of time with a combination of conjecture and real calculation trying to work out what the decay is to the new vacuum. And in the simplest of all worlds, that energy difference going from having the brain to having no brain should be equal to the tension of the brain. And so, in some situations, and with the right calculational technology, which can't just be string perturbation theory because it's moving between, so you have to go to string field theory and stuff like that. It should be that a first principles calculation should tell you that the tension of the tachyonic brain should be equal to that mass difference of going to the new vacuum. Exactly. Right. So good. Yeah. Let me just, connecting to some of the stuff we did here. I focused on the BPS sector, right? The other thing that you should know about BPS is that it's simply I have some extended supersymmetry, and I pick some state in which half of the supersymmetries are broken. So I have an n equals 2 theory, for example, the type 2A or the type 2B, and I put a BPS state in, which is a D brain. I put some open string sectors in, and we know open string sectors have n equals 1. And so that's exactly what that BPS language is telling you about. There's a whole other sector. I could have created brains that were not BPS states, that were carrying, for example, the wrong Ramon charges, or just not having the right balance between Ramon charge and Nova Schwarz charge. And those guys would have a tachyon associated with them, generically speaking. Not all, there are ways of, and so again, you can have this story where those guys are unstable in the theory and decay off to some new vacuum that you could attempt to follow. So I made our life simple by making sure that we always preserve some supersymmetry in our discussion so that we didn't have to worry about stability issues.
Okay. Another question, is there a polytrope analog to the...
Very good question. I actually don't know what the answer is. Do I know the answer? I don't know.
Okay, so instead of that, I guess one more.
No. Someone else might have a question. Also, we're running out of time. One brief question, and then we're going to spend an hour and a half answering the questions anyway. Yeah.
Could you then tell us something about the relation between tension and charge, the physical meaning? I don't know how should I interpret that if example, if the coupling strength goes to 0, then the tension goes to...
Oh, very good. Okay, let me briefly answer that, but this is something that's worth picking up in the Q&A. But let me... good. Yes, I should have said a lot more about this, but didn't have a lot of time. And I did promise. But first of all, the physical interpretation, the fact that it carries charges and has tension. Now, I gave you the Reisen-Nordstrom example, right? And now I've actually shown you explicitly that this, this is an example of that. And had we time, the other thing I would have done is prove to you that this was actually secretly made of D-branes, but I don't have to. So it's a thing that has the same tension, same charge, so it kind of has to be. But there's a beautiful probe calculation you can do that shows that. Anyway, so that's the physical interpretation. But there's an extra piece of physics, which is the fact that this tension goes inversely with the string coupling, which I had promised. It's one of the reasons that, in some sense, we miss these guys. I forgot where I'm looking. Oh yeah, it's one of the reasons we actually miss these guys, right? Because in string perturbation theory, they're very heavy. Yeah, we're expanding around G string equals 0. So 1 over G times a number is the tension. We're not really turning these things on, so we're not really seeing them show up in string perturbation theory in loops or what have you. So we might as well have them turned off, which is what we were doing for decades. Okay? The other nice thing is the fact that they go inversely with the tension, and the fact that, as I promised you, if they're BPS states, certain computations about them can be trusted. It means that I know what the tension of that thing is, even if I go to large G string. And at large G string, it's becoming lighter and lighter. And this is now the origin of the thing I said over here, which is that string theory fully is not a theory of strings. At weak coupling, yes, we start out with strings. Then we discover that there are these objects with mass that goes like 1 over G. Now I go off, in the full theory, I should also tune the coupling and go off to strong coupling. What I'm seeing is that new dynamical objects of higher extent are becoming light, and they could take over the dynamics of the theory and actually make the string not be the important thing anymore. So that's the basis of saying that string theory isn't really a theory of strings in some sense. Okay, and that's probably... Yeah.